Hello, today I'd like to do a numerical example of Gauss-Seidel. So Gauss-Seidel or Jacobi, these are iterative methods that allow you to guess the solution to a linear system of equations of ax equal b, where a is a square matrix, x is a column vector of unknowns, and b is a column vector of knowns. There are two bounds on the floating point error. So our error would be ax minus b. I'm going to call it the one norm. So that's our error, and we want to know what's the bound on that error, the floating point error bound. And there are two methods. There's the Griffiths method here that we learned in our theory video, and then there's the submultiplicative bound that we learned in our theory video. Okay, so we have those bounds on floating point errors. But also we might think about a polishing condition which looks for changes in x. So if you look at relative changes in particular x coordinate, then you'll have an array of those relative changes in x coordinates. And you look at what the maximum might be, so that's an infinity norm, and it's going to be less than or equal to some what I call the book stopping criteria. So this is somewhat arbitrary, so there's this last one, the polishing condition, a little bit arbitrary on what that E sub s might need to be. But we're going to look at one complete iteration by hand so you get a feel for what goes where in this whole idea. So if you haven't seen the Gauss-Seidel theory video, make sure you watch that first. Okay, so here's our example of Gauss-Seidel. So we're looking at it's actually from the homework. It's a diagonally dominant matrix, and we're looking for the solution of x1, x2, x3 that gives us this right-hand solution vector. So x1 is 3, x2 is minus 2.5, and x3 is 7. So we know those are the actual correct answers, but what we're going to do is we're going to start just a little bit away from that. Okay, we're going to start a millionths away from 3 for our x1. We're going to start a millionths away from our minus 2.5 for x2. And we're going to start a millionths away from 7 with our x3. And we're going to look at how close that is to being a solution to within round off error. And so we're going to say that, hey, let's say our k iteration counter is 0, so that's going to be really our starting position. So the first thing you're going to do is calculate the floating point difference or the error, the E. So that's going to be ax minus b. So there's my a, here's my x is 0, and here's my b. And when I calculate, do the matrix multiplication and carry this forward, I get these three E1, E2, E3, my errors that represent how close these three values are to the correct answer. So when I do the one norm of that, I basically take the absolute value of each one and add those up, and I get a number that looks like this. So this is indicative of how close x is, this x column vector is to a solution to ax equals b. Okay, so keep that in mind. This is the actual code that I use to get that value of the E vector coupled with the one norm of it. I basically started with A, B, and those three x values, x1, x2, x3, being close to 3 and 2.5 and 7. And then I carried through the A times x minus b to get my E sub k, I called it, EK. And I did a matrix display of that gave me 16 decimals to the right of the decimal, or 16 digits to the right of the decimal. And then I showed the one norm in this way. Okay, so that's how I got the numbers that I showed you on the previous slide. So now let's go see about what the the floating point bound might be for this. So I'm going to do the Griffiths test. So what I'm interested in, I just calculated this. What I'm interested in is what is this right-hand side for the Griffiths method? Okay, so what is that right-hand side? So that right-hand side, remember from the theory, I'm using the scalar n. In this case, it's 3. So 3 plus 1 is 4. So I'm going to have that. And then I'm going to look at A, absolute value of that A matrix. That's going to be each component absoluted. And then I'm going to absolute each component of X. And then I'm going to absolute each component of B. And do this matrix multiplication, scale by 4, and then add the B. Take the 1 norm of that and multiply by machine epsilon. So that's kind of the flow of it for the Griffiths calculation. So the first thing I'm going to do is look at this. So I set that up. I've got the 3 plus 1 because n is 3. There's my A matrix. I haven't taken the absolute yet, so I've got it inside the vertical bars. I've got my X inside the vertical bars. I've got my B inside the vertical bars. And then now I take the absolute value. So now everything that was negative changes to positive, including that one and including that one. So now I carry through that matrix multiplication here, scale by 4, add the B, and I get that. So that's the array that's inside the 1 norm. And then I need to take the 1 norm of that, of course. So I'm just adding these 3 things up, and I get 506. So kind of how I look at it, I like to know what is scaling machine epsilon. Because the thing that scales machine epsilon, that is indicative of how many floating point operations is being estimated here within the Griffiths method bound. So then to get the actual bound, I do need to multiply by machine epsilon, and we're going to use 2 to the minus 52 for that. So when I take 506.35 and multiply by 2 to the minus 52, I get a value that is 1124, way over on the right, most digits past the 16 digits past the decimal point. Okay, so that is the Griffiths method bound. And then what we're going to do is show how to calculate that. So I did 4 times abs of B times abs of xk plus the abs of B. And that's how I generated this and then showed the 1 norm and then the 1 norm times eps. So that's how I generated the numbers that I just showed you. Okay, so now the question is, remember that my error, the left-hand side is rather big in comparison to the Griffiths error bound. So I'm going to just kind of take a look at this a minute. Remember the Griffiths error bound, I've got the 1124 way over here. So this AX minus B, the 1 norm of that, is way, way, way bigger than that Griffiths bound. So it fails the Griffiths method test. It's not a root according to the Griffiths method test. Okay, so very, very, very stark, very, very far from being a root to within floating point error. Okay, so now let's take a look at the submultiplicative test. So for that one, we're going to be interested in getting this right-hand side now, and we're going to get the thing that scales machine epsilon first. So what we're going to do is kind of build it like this. We're going to look at the 1 norm of the matrix. That's the first thing. So I've got the 1 norm of that matrix. Remember, that's max column sum. So go in here and get the 1 norm of each column. And you can see here that's going to be 3.4 when you look at the absolute value, sum the absolute value, 1 norm, summing the absolute value of each of the elements. Here it's going to be 7.3, summing the absolute value of the elements, 7.3. And then here is 10.5, summing the absolute values of the elements. And then you look at the max of that, and that's going to be the 1 norm of the whole matrix. And then you do a similar thing for x1. You look at the max. You look at the sum of the absolute values. So you're going to have the 2.999, and then you're going to add in the 2.5 and change plus the 6.99. You get about 12.5 for that. And then you do the same thing for the B. You're adding the absolute values of each of those components to get 98.55. And then I start putting it together, so it's really easier, quite frankly, to get the submultiplicative bound because you're doing the one norms, which are very, very straightforward to do. So I've got 10.5 for the A1. I've got 12.5 for the X, one norm of X, and then 98.55 for the one norm of B. Add those, or add that up, multiply these two together by submultiplicative, add that in, and I get 229. So that's kind of giving me an idea that's 229 floating point operations is sort of the bound. So I take that and then multiply by 2 to the minus 52, and I get the 510 way over here on the right hand. So that's going to be the submultiplicative bound, and this is how I calculated it. Very, very, very straightforward. All in one line there to get my submultiplicative k bound, and then I multiply it by eps. So that's how I got it. And then the question is, does that error, the one norm of the error, is that less than the submultiplicative? Well, heck no. I mean, the submultiplicative is actually smaller, tighter than the Griffiths method bound. So this is even further from being a floating point, passing a floating point test. So it is way off, even though it looks really, really close. So it's not a root. Okay, so now we're kind of thinking about Gauss-Seidel. So to do a complete iteration, I kind of want to look at, well, where the next x is going to be, x1, x2, x3. So this is how I actually did it, showed it in class, is that the next x1 depends on the previous x2 and the previous x3, and then of course you got the a's that are coming from your A matrix, and then you got the B from your B column. So the way Gauss-Seidel works is that the x1 of the next iteration depends on the previous x2 and x3, and then the x2 will depend on the new x2 will depend on the newest x1 coupled with the older x3. Again, using the A's and B's of the A's of the A matrix and B of the B column. And then the last one is the x3 is going to depend on the newest x1 and the newest x2. So Gauss-Seidel, you're always using the newest x that you have, that you've calculated so far. So that's the idea, but this was built on getting a k from a k minus 1. What I'd like to do is to refactor those equations so that I'm getting the k plus 1 x1, x2, x3 from the k x1, x2, x3. So the k plus 1 x1 will depend on the k x2 and the k iteration x3. And then the k plus 1 x2 will depend on the one you just calculated for x1 and the old version of x3, the k version of x3. And then the x3 finally will depend on the newest x1 and the newest x2. So just kind of shifting so that I'm getting k plus 1 from k. And I'm going to do that now. So originally our k was 0. We started at 0, and we had those x1, x2, and x3 that were just a millionth off of the correct answer, which was 3 minus 2.5 and 7. And I want to know, well, what would Gauss-Seidel say would be the next x1? And so to do that, I bring in the values from our matrix and our A matrix and our B. I bring those in. A11 is 3, so I've got that into the denominator. The B1 is 7.85, so I've got that there. A12 is minus 0.1, so I've got that there. And then I'm going to be bringing in my x2 of the kth iteration, so that's going to be minus 2.50000, whatever, 1. And then I'm subtracting a1, 3, which is minus 0.2, beg your pardon, times x3, which is the 6999999. All right, so I carry out all that calculation, and I get 2.99. I get the same thing. It's so minutely changing. I've got a 2 all the way in the 16th place, but it is actually going towards the correct answer, which we know to be 3. So that was what the x1, how the x1 would change. I'm going, well, crap, that's kind of minute. But then I went and did x2. The next x2, of course, will depend on the newest x1 and the oldest x3. With the values to be 2, for example, minus 19.3, A22 is 7, and then of course I have the A21 and the A23, A21 and A23 that I'm bringing in, coupled with the X1 and the X3, the X1 of the newest with the old X3. So I get something that is a little bit bigger jump than what the X1 actually changed, but I am going towards the actual 2.5. So this is reducing towards the 2.5, because remember that 1 that you see here would be 1, 2, 3, 4. It'd be right there. So we are diminishing towards that 2.5 very nicely. And then the X3, we're using, again, the very newest X1 and the newest X2 that we've just calculated. And now the next X3 actually shot above 7. But if you think about it, 1, 2, 3, 1, 2, 3, we're much closer to the answer of 7 than we were earlier, because we were a millionth off. Now we're much closer than a millionth away from the correct answer of 7. So very interesting how the steps have changed. Let's see what the error looks like now. Remember from previously at our 0 iteration with these values, we had an error, 1 norm of the error that looked like that. So let's see what it looks like now. So if we bring in at k equal 1, we're going to have our x1, x2, and x3 looking like that. Remember, we know that the true values are that. But let's look at the k equal 1 iteration, what does our errors look like? So we bring in our matrix, we bring in that new solution, proposed solution vector, and we get an error that looks like that, an error array that looks like that. And when we take the 1 norm of it, we're going to get an error, a 1 norm of the error that looks like that. Now, we want to see, is this diminishing? Is this diminishing? Before we had, the 196 over here in that location, and now we've got a 596, but that's actually going to be better. It's going to be much better. We're going to be order of magnitude, maybe almost 2 orders of magnitude better. We reduce significantly the error that where we had before, driving that towards 0, which is what we would want, right? To find that x vector that would do that. Okay, so feeling pretty good right now. I see that the Gauss-Seidel, yea verily, is marching towards what we know to be the true answer. We see that our 1 norm of our error is reducing. It's just not to within floating point error yet. So there's a lot of room to improve this for sure. But one thing I wanted to do next is to look at what this book polishing type situation would look like. Remember that with k equals 0, we had these values, and then with k equals k equals 0, we had that, and with k equals 1, we had these values. So what I want to do is look at the relative difference in how these x values, these 3x values, have changed. And you can see very clearly how I've done it. I've used the equation from the book, the relative difference between the k iteration and the k plus 1 iteration, k and k plus 1, and then you divide by the new value for each of these. You do the same thing, and you can see what I have for the the epsilon sub a for the 1, the 2, and the 3. And then what you're doing for the infinity of this, the infinity norm, you're actually going to take the maximum, and it turns out it's going to be, this one's going to be the maximum. Okay, so what is really weird about this is, you look at the epsilon sub s from the book, and you do see that this value is not less than that epsilon sub s value, but it's pretty damn close. It's only 3.8 or so times bigger. The next iteration likely would satisfy the book polishing thing, which is the only thing the book uses actually, but we see that we're quite a ways away from having a solution that is accurate to within floating point round off error. We see that. So this caught me by surprise, quite frankly. So we did one complete iteration of Gauss-Seidel for a diagonally dominant system. We looked at the floating point round off for Griffiths method. We looked at the submultiplicative bound, and neither of these were we remotely close to having a solution. But when we looked at the book polishing check, that was pretty damn close. So what the lesson is here is to really look at tightening those bounds, if you will, and really looking at what floating point round off error bound might look like, and then comparing your error to that. So I hope you enjoyed that.